Good day everyone, I am Mokshit. Today I will be presenting my course project for DA623 on speaker recognition using neural networks. This project explores how deep learning can be used to identify speakers from their voice patterns with high accuracy. Identification is the process of determining which registered speaker is talking from a set of known speakers. Unlike speaker verification, which confirms the claimed identity, must be selected from the correct speakers from multiple options. The key challenges in this field including handling variability in speech due to emotional states, health conditions, background noise, etc. Additionally, speaking style variations between fixed phrases and spontaneous speech create further complexity. These challenges make the speaker recognition an interesting machine learning problem that requires robust feature extraction and modeling. My implementation follows a pipeline approach. First, I collect audio samples from multiple speakers. Then these samples undergo pre-processing and data augmentation to improve model's robustness. Then I transform time domain audio signals to frequency domain using fast Fourier transform to extract spectral features. These features are fed into a convolutional neural network with residual connections for classification. The model outputs probability distribution across speaker identities with high with the highest probability indicating the predicted speaker. Now, data augmentation is crucial for robust speaker recognition models. I added controlled background noise at a different signal to noise ratio. This helped the model to learn more invariant features that persist despite acoustic variations. I used a dataset containing speech samples from five different speakers, augment it introducing various background noises like ambient sounds, etc. And this expanded the effective training set and improves model ability to generalize to real world conditions where clean speech signals are rare. The fast Fourier transform is essential in my pipeline as it converts the time domain audio signals into frequency domain representations. This transformation reveals the spectral components that are critical for analyzing vocal characteristics are unique to each speaker. By applying fast Fourier transform, we can identify patterns in pitch, harmonics that serve as distinguishing features. These frequency domain features often provide more discriminative information than the raw waveforms, making them ideal input for neural networks. In my implementation, I extract the first half of the FFT, which contain the positive frequencies, providing a rich representation of speaker-specific characteristics. My model uses CNN architecture enhanced with the residual connections. The input FFT is passed through the n number of residual blocks with each convolutional layers, batch normalization, and ReLU activation. These residual connections will help preventing vanishing gradients, making it easier to train the deeper models effectively. Each block uses varied filter sizes, pooling layers to reduce dimensionality while preserving key spectral features. This allows the model to capture both local and global patterns in the frequency domain. After feature extraction, the output is flattened and fed into dense layers, both using ReLU activation. These layers learn high-level abstractions and serve as the final classifier for speaker identification. The to optimize model performance, I conducted systematic parameter sweep to find the best possible architecture. Now this slides show. Now I built an interactive training interface in my Jupyter notebook that allowed for my real-time experimentation with different architectural parameters. This approach enabled me to efficiently explore the hyperparameter space and understand which aspect of the model were most important for the performance. To better understand how well my model separates speakers. I use a TSN plots to visualize the high dimensional FFT spectrogram features in 2D space. The first plot is colored by the true speaker labels. You can see the clear clusters, which mean the model's learned features effectively group samples from the same speaker together. The second plot is colored by the model's predicted labels. The clusters largely match the uh, true labels, showing the model's prediction align well with the actual speaker identities. This visualization gives me qualitative evidence that the model is not just memorizing but actually learning meaningful speaker specific representations from the audio data. Such features space visualization are also commonly used in multimodal learning research to compare how well different modalities of or model architectures operate classes. In my project, TSNE helped me to confirm that the FFT-based features and the CNN architecture together enable strong speaker discrimination, which is crucial for robust speaker identification tasks. While my project primarily focuses on the audio-based speaker recognition, it connects with the multimodal learning in several important ways. Modern speakers recognition are increasingly incorporating the multiple modalities, such as combining audio features with the visual representation from the lip movement and facial expressions. Research papers like speaker recognition in realistic scenario using multimodal data demonstrates integrating facial information with the voice data significantly improves identification accuracy. Now, the VGG model I referenced here uses a deep CNN architecture similar to the mine but expanded to handle multiple input streams. My project could be extended to the multimodal context by incorporating visual data alongside audio features, potentially using a two-branched network architecture, which I shown in the previous paper, where separate pathways process a modality, different modalities before fusing their representations. The TSNE visualizations I created, I shown here, shows how features from multimodal approaches compared to the single modality approaches, revealing clear clusteral patterns when multiple information streams are combined. This connection illustrates how even single modality work like mine fits into the broader multimodal learning landscape that we have studied throughout this course, where contemporary information sources can be leveraged to improve model performance on challenging recognition tasks. Thank you. This course, the computing with signals course, made me go through various projects and various concepts in the signal processing in the audio and visually, and it also helped me how to learn how these features along with the incorporating neural networks can significantly come up as a real life projects which we can use daily. I would like to thank our Professor Neeraj Sharma for explaining such concepts in a clearer way. Thank you.